Good morning. Welcome back to Stat 218. Today we're going to start in on the concept of a hypothesis test. Ending up with a brief discussion of the t-test, and we'll be set up for the ability to tackle some of the homework questions out of Chapter 7. Let's start with contrasting a hypothesis test and a confidence interval. You might want to write this down. A confidence interval is an attempt to answer a numeric question with data where you would estimate an unknown population mean or an unknown population parameter with a margin of error attached. A hypothesis test is an attempt to answer, again with data, a yes or no question. If your natural question is answered with a yes or no, for example, is Donald Trump currently ahead in the presidential election? The answer would be yes or no. So a hypothesis test would be the approach to answer that sort of a question. So conceptually, I want to get into the concept of a permutation test, and we're going to do this via thought experiment rather than actually doing it with software this term. Again, changes due to a virus. But ask yourself, with the chocolates and the vanillas, perhaps the two different flavor categories of ice cream, we tackled in Chapter 6 the question, how many more calories does chocolate have on average than vanilla? We attempted to answer that question by saying about 10, but there's a margin of error of plus or minus, and then we gave you that confidence interval, a range of plausible values for how many more calories chocolate has than vanilla. In a permutation test, it's a little bit different. Permutation test, excuse me, in a permutation test, what we're going to do is tackle the question by asking, what if the flavor category, vanilla or chocolate, were assigned at random to each of the different calorie counts? Again, we're going to permute the actual flavors across the actual calories. There were a collection of calories, some were very caloric, 270 calories per half cup serving. Some of them were not, 110 calories per half cup serving. And we're asking ourselves, what if we had just assigned 17 of them to be called chocolate at random, and the rest we had called vanilla? Again, the rest of them, which were not chose at random, it's essentially as we're saying, we chose 17 at random to be called chocolate and 18 at random to be called vanilla. And then if we were to calculate the two separate population or two separate sample means and ask ourselves how different could they be, sometimes the difference will be 0. Sometimes the difference will be quite large due to just bad luck in which group was assigned to be called chocolate versus vanilla. Now, if we were to do that over and over and over and over and over and over and over again, we end up with something that is mathematically almost exactly equal to the method we're going to be introducing today, a t-based hypothesis test, a test statistic that we're going to call the t-test. So let's get after it. The confidence interval tackles the question, what is the value of mu chocolate minus mu vanilla? We're going to tackle the question today, how many more calories is the value of chocolate on average different than the value of vanilla on average? Again, note the yes or no answer. The hypothesis test has 5 parts to it. Turns out that our book says there are 5 parts to a hypothesis test. Many books have as many as 8 parts of the hypothesis test. Some books have as few as 3. Our book goes with 5. I'm just saying whether it's 3 or 8 or 5, they're all the same. We could basically take one of our steps, the first step, the hypotheses, and split that out and call it 2 separate steps. Now, I've crossed out here in the notes the level of the test. We're going to start with a level of the test being 0.05. If we want to later on relax that and have a different level of the test, we will be able to do that. But right now, we're going to start with just a 0.05. Basically, if you have a lot of moving parts, it's easier to learn what's going on with fewer moving parts and then sort of give yourself a little bit of grace and then sort of dive in with a more complex problem. The level of the test is sort of like driving a stick shift as opposed to driving a manual transmission. Let's work on the manual transmission first. So, does chocolate have a different number of calories on average than vanilla? The null and alternative hypotheses are ways of writing down our yes and our no. So let's write that down. Let me grab my glasses so I can see. Null hypothesis. I'm going to call the H sub 0 for the null hypothesis. H sub A is the alternative hypothesis. Now, typically, the natural question is going to be the alternative hypothesis. Not always, but typically. Also, the alternative hypothesis cannot have an equal in it. So I'm going to write mu chocolate and mu vanilla are not equal. The logical opposite of the alternative hypothesis is the null hypothesis. The mean number of calories in chocolate is equal to the mean number of calories in vanilla. Notice there's an equality in our null hypothesis. The alternative hypothesis cannot have an equality, and they give us 2 different theories for reality. Theory number 1, they are the same. Theory number 2, they are different. And the data will then speak to the question of which of the 2 theories we ought to be believing. What sort of data would convince you to believe the alternative hypothesis over the null? Again, the null hypothesis is what you're going to say you will be believing until you're convinced by the data that it's wrong. If you're convinced by the data that the null is wrong, you're welcome to believe the alternative hypothesis. It's almost like a jury. The jury is instructed by the judge to presume innocence until guilt has been demonstrated. What sort of data would convict the null hypothesis? I'm thinking that if we have the 2 separate sample means very far apart from each other, that would be convincing to me. If the 2 separate sample means were so far apart that that you're saying that should not have happened just by dumb luck alone, it must be reflecting a real trend that the population means are different, I would be willing to believe the alternative hypothesis. So, in a hypothesis test, our potential conclusions are the alternative hypothesis. If the data are very unlike what you should have seen, just by luck alone, had the null been true, or else you say the results are inconclusive. You would never say the null is true. You'd say just that we cannot conclusively conclude the alternative hypothesis is superior. Okay? Again, you never conclude that the null is correct. You just say it's not clearly wrong. Okay, so here's the way we're going to sort of outline that next step in a hypothesis test. The hypothesis test always will have a test statistic, which always is a measure of how different the data are from what you would expect the data to be if the null hypothesis were true. So I've written that out downstairs. Three different formulations of that exact same statistic based on the three different ways of writing a standard error. Okay, so in the first version of the equation, I'm comparing what the data say to what they should say if the null were true. The difference of the sample means should on average be about 0. Sometimes it will be higher than 0, sometimes lower than 0 just by luck, but on average, if the two population means are identical, then the two sample means on average should equal 0. So we're going to divide that through by the standard error. Which tells us how different our estimate is from what we're attempting to estimate. So how different is the estimate for what we're attempting to estimate? Here's the estimate. I'm sorry, here's our estimate. Apple Pencil troubles right now. Okay, so what we're attempting to estimate is mu1 minus mu2. Our estimate itself is y bar 1 minus y bar 2. How different is that from the number mu1 minus mu2? That's a standard error. So the second two formulations of the equation are, if you're not given the standard error for the difference by itself, you might be given the separate standard errors for each of the two separate sample means. You could square those and sum those. Not hard. Okay. Another approach that you could take is to, if you don't have the separate standard errors, you'll almost certainly be given S1, S2, N1, and N2. In which case you could use the calculate the standard error by yourself for fun approach. Okay, so let's dive in on our example with vanilla and chocolate. With vanilla, we've got 18, okay, as our sample size. The average, okay, 165.56, and we have the standard deviation given to us right there. But we also have the standard error, so that's sort of nice. We could probably work with that. For chocolate, there's 17 of them, averaging 174.7, a standard deviation of 44, and then we have a standard error given to us, 10.7. So let's get after how to tackle that problem. Our test statistic T is found by just doing the plug and chug. My null hypotheses are vanilla and chocolate are the same on average alternative, that mu is different between the two groups. Mu1 and mu2, they're different. Here's a little typo, sorry about that. Cross that out. Our test statistic is a matter of plugging in the separate sample means minus 0. Again, the minus 0 is algebraically superfluous, but the minus 0 allows us to say, essentially, we're comparing the difference of the sample means to what the difference of the sample means would, on average, equal if the null were true. Divide through by our separate standard errors squared and summed. I've got a 0.66. That's not so bad. I've got a 0.66 test statistic value. Where do we go from there? Well, we need to do a calculation of what we're going to term the p-value. And that's based on degrees of freedom, like before, or you could just use the shortcut like we've talked about. But the p-value is what The p-value is a measure of how likely is we'd see data like what we did see if the null were true. Literally, the p-value is the chance of seeing data like those that we saw, or even more extreme, just by luck alone, if the actual, in fact, population means are identical. You can see here the p-value sort of shown graphically. The p-value is the area above the absolute value of t and below the negative of the absolute value of t. What we did get in our test statistic t is a measure of how close the data are to the null hypothesis, a measure of how more unlikely would be more unlikely upstairs and more unlikely downstairs taken together. So the p-value, that's going to be easy to calculate. Let me see if I can grab that for you. The p-value is found again with degrees of freedom, and we have 17 chocolates and 18 vanillas. Our shortcut approach says we should be using 16 degrees of freedom in our t-table. Okay, and our test statistic was 0.66, if I remember correctly, 0.66. Okay, so all we have to do is to use the t-table to bracket our test statistic by values where the upper tail area is known. So I had a 0.66. Let's drag our t-table over here, and maybe bigification would be a good thing to do because that way we can see more easily. So in the row that has 16 degrees of freedom, that's down at the very bottom, 16 degrees of freedom. I'm wondering where a 0.66 would occur. So in this bottom row, below the line, below the line that I'm trying to draw, in the not quite bottom row, I'm going to circle this row. Where would 0.66 belong? I'm noticing that it's not here anywhere. But if it were to be in that bottom row, it would be off to the very left. 0.66 would be way the heck down there. So if I were to read to the top, the upper tail area isn't 0.025, 0.050, 0.010. Notice as we move to the left, the upper tail areas get larger and larger and larger. Our upper tail area is greater than 0.10. Our upper tail area is greater than 0.10. But we need not just the upper tail area, we need the lower tail area. We've got the upper tail area above a 0.66, which is greater than 0.10, but we need to add to that the area below a negative 0.66, which is also greater than 0.10. So our p-value is greater than 0.20. Not so bad. My p-value more than 0.2. And from the table, we can always get to a p-value that allows you to hit your conclusion. So let's move towards a conclusion. Our p-value is greater than 0.2. A different t-table that I have sometimes used in class has the p-value greater than 0.4. I'll go with greater than 0.2 or greater than 0.4. In either case, our p-value is certainly above alpha 0.05. Alpha is the cutoff, if you will, the significance level of a hypothesis test. And because my p-value is more than 0.05, I'd say these results are inconclusive. If you will, there's not enough evidence to say that vanillas and chocolate are different on average. There's not a statistically significant difference. That is your conclusion right there. Any way you want to phrase it works for me, as long as it's technically correct. Our data do not conclusively demonstrate a difference between our two groups. Okay, so what if our p-value had been 0.03? If our p-value had been 0.03, the p-value would have been less than alpha, and I would say, aha, we do see a statistically significant difference. In our case, we don't see a statistically significant difference, but if the p-value had been below alpha, 0.05, we would say that there is a statistically noticeable difference. Okay, so it's pretty straightforward. If I want to use software, or you guys have, some of you, fancy calculators, that's absolutely okay. I will sometimes be using the software for the purpose of demonstrating something, but again, this term, virus, we're not going to be doing any calculations with the software that are required. Okay, but our conclusion, straightforward. Okay, good place to stop for the day. Enjoy the rest of your day, and we'll see you in the future.